Welcome to the deep dive. Today, we're embarking on a kind of cosmic weighing session.
Right here in our own backyard, cosmically speaking.
Exactly, our galactic neighborhood, the local group. Now, this isn't, your average street. It's this sprawling collection of, what, about 80 known
They're
galaxies.
around 80, yeah, stretching across something like 3 megaparsecs, which is, well, it's vast.
Mind-bogglingly vast. A megaparsec is about 3.26 million light years, just to give you a sense of scale.
And the real heavyweights in this group are us, the Milky Way, and our big neighbor, Andromeda, M31.
Both giant spirals, right? Packing something like 1 trillion times the mass of our sun each.
Roughly, yeah, massive. And they don't travel alone. They both have these entourages, systems of smaller satellite galaxies.
Including some really faint ones, these ultra-faint dwarf spheroidals.
Exactly. So for the Milky Way, think of the Large and Small Magellanic Clouds, Sagittarius, Draco,
Mm,
Carina, Sextans, Fornax.
our little companions. And Andromeda has its own posse, too.
It does. M32, M110, NGC 147 are some of the main ones hanging out around Andromeda. There's actually a pretty good list on Wikipedia if you want the full rundown.
Right. What's really interesting, though, is how this local setup, this sort of clump of galaxies, becomes this amazing testbed.
Uh-huh. A testbed for understanding the whole universe, really. It's like a mini cosmos right here.
It lets us ask these really fundamental questions about how galaxies form, how they interact.
Precisely. And that's really our mission for this deep dive, isn't it? To dig into how scientists are actually figuring out the total mass of this local group.
Using the research we've looked at, yeah.
Yeah.
And why getting that number right is so important for cosmology.
Because it's not just a number, is it? It tests the basic rules, the physics governing how everything formed and evolved.
Weighing our neighborhood to test the universe's laws. And this term, local group, it's been around a while.
Oh, yeah. Edwin Hubble himself coined it back in 1936.
Wow, standing on the shoulders of giants then.
We are. And we'll be looking at some pretty clever ways they estimate this mass. Things like cosmological simulations.
Running whole universes in computers.
Kind of, yeah. And also this thing called the timing method, tracking how galaxies move.
Okay, and I hear new data, especially from that Gaia mission, is really shaking things up.
Big time. Gaia's giving us such precise measurements. It's refining everything and even, challenging some older ideas.
Okay, so to really grasp our neighborhood now, sounds like we need to look back at the family history of the big two, Milky Way and Andromeda.
That's a good way to think about it. And their histories involve a lot of, well, acquisitions.
Acquisitions, you mean eating other galaxies?
Pretty much, yeah. Our own Milky Way has been doing it for billions of years,
Hmm.
devouring smaller nearby galaxies. Galactic cannibalism, basically.
Sounds dramatic. And Gaia, that's the European Space Telescope mapping stars, right? Gaia's helping us see the evidence.
Absolutely. Gaia's measurements are so precise, we can actually see the leftover debris streams from these past mergers, like cosmic breadcrumbs.
So it's not just theory anymore. We see the proof.
We see the proof. It helps us piece together the timelines, like forensic evidence in space.
What kind of evidence?
Well, there's the Gaia Enceladus stream, evidence of a big merger about 10 billion years ago that probably helped form our galaxy's thick disk. That was work by Helmy and others.
10 billion years ago.
Wow. And then there's this phase space spiral structure in the star's movements, and Toja and colleagues link that to a more recent brush with the Sagittarius dwarf galaxy, maybe 300 to 900 million years ago.
Like reading tree rings, but for galactic history.
Kind of, yeah. And Andromeda has its own stories, too, not just us.
No, like what?
There's evidence suggested by D'Souza and Bell for a really dominant merger in Andromeda's past, maybe around 2 billion years ago.
And what did that do?
Well, it might explain some weird things about Andromeda, like its compact little satellite M32 that could be the stripped core of the galaxy it merged with.
The leftover heart of the victim galaxy.
Possibly. And it might also explain Andromeda's interstellar halo and this huge stream of stars they see around it. Clues to a past upheaval.
So understanding these histories is key.
It's absolutely crucial because any good cosmological model, any theory about how the universe works, has to be able to reproduce these kinds of details we see right here in the local group.
It's the ultimate reality check for the theories.
Exactly. If the models don't match what we see nearby, then we're missing something important.
Okay, so how do we weigh this whole cosmic neighborhood? I can't exactly use bathroom scales, can we?
Oh, no, definitely not. It's more indirect. Scientists use what they call tracer objects.
Tracers, like what?
Things orbiting within the local group, like stars in the outer halo or those satellite galaxies we mentioned, or even globular clusters.
And how they help.
By tracking their movements really, really precisely, their positions, their velocities, you can figure out the gravitational field they're moving in.
Ah, so their motion tells you how much gravity there is, and gravity comes from mass.
You got it. You work backward from the motions to the mass distribution that must be causing them.
And this ties into dark matter, I assume? That invisible stuff that makes up most of the universe's mass?
Absolutely central. The standard model of cosmology, lambda CDM for short, predicts that dark matter should be clumped around big galaxies like ours and Andromeda, forming these huge invisible halos.
And the satellites orbit within those halos.
That's the picture. In fact, predicting that galaxies like ours should have lots of these dark matter satellite halos was one of the early successes of CDM. Discoveries over the last 20 years have largely backed that up.
But I feel a but coming. It's not perfect, right? CDM has some...
That's right. As observations get better, we find these little discrepancies, these tensions between the model's predictions and what we actually see. Paravolaropoulos and Skar wrote a whole review on them.
Tensions? Like what? Give me an example.
Okay, well, one interesting one is called the too big to fail problem.
Too big to fail. Sounds like banking, not cosmology.
Huh. Yeah, the name's catchy. Basically, simulations based on ACDM predict that orbiting the Milky Way, there should be more massive dark matter subhalos than the number of great satellite galaxies we actually observe.
So the simulations predict big clumps of dark matter that should have formed stars and become visible galaxies. But they didn't. They stayed dark.
Something like that. Or the ones we do see seem less dense in their centers than the simulations predict for halos of that size. It's a mismatch, identified by Boylan-Kolchin and others back in 2011.
So these tiny satellite galaxies are actually poking holes in our big picture model.
They're certainly providing crucial tests. It forces us to maybe tweak our ideas about dark matter or how galaxies form within these dark matter halos.
Which brings us back to the mass of the local group. Getting that right is a really powerful test.
Exactly. It constrains the whole cosmological framework. And two main methods really stand out for estimating that mass.
Okay, what are they?
Cosmological simulations, which we touched on, and the timing method.
Right, let's dive into the simulations first. Creating virtual universes still blows my mind.
It is pretty amazing. They model the physics of gravity, gas dynamics, star formation, dark matter, everything, starting from the early universe and letting it evolve, like the EGLE simulations, for example.
And then they look for virtual local groups.
Sort of. They look for simulated galaxy pairs that resemble the Milky Way and Andromeda system. Then they compare the properties of the simulated satellite galaxies around those virtual giants.
With the real ones we see, like the Magellanic Clouds, Draco, Ursa Minor.
Exactly. Using those super precise Gaia measurements for the real satellites, their full 6D positions and velocities.
And if the simulation matches reality,
then the total mass assigned to the Milky Way and Andromeda halos in that particular simulation is likely a good estimate for the real mass. Different groups have used this approach, Carlesi, Limos, and others.
It's like finding the right recipe by baking lots of slightly different cakes and seeing which one tastes most like the real thing.
That's a decent analogy, yeah. Now, the other method, the timing method, has a really interesting history.
Okay, tell me about the timing method.
Well, the basic idea goes way back. It assumes that the Milky Way and Andromeda started out pretty close together just after the Big Bang.
Right, everything was closer back then.
Exactly. And since then, they've been moving apart because the universe is expanding, that's the Hubble flow, but their mutual gravity has been pulling them back together.
So it's a tug of war between cosmic expansion and gravity.
Precisely. And the timing argument says, if we know how far apart they are now and how fast they're moving towards each other now, and we know how old the universe is,
we can calculate the total mass needed in the system to make that specific history happen.
That's the core idea. It's like knowing where a ball is now and how fast it's falling and using that to figure out the Earth's gravity. Kahn and Wolcher first formalized it in 1959.
But that sounds simple. Did they assume they were just moving straight towards each other?
The original version did, yeah.
Yeah.
Assumed a purely radial orbit, but that was refined later. Anaisto and Lyndon Bell showed in '82 that you could actually solve it analytically, even if Andromeda had some sideways motion, some tangential velocity.
Which it almost certainly does. They made it more realistic.
Much more realistic. And it's been refined even further since then.
How so?
Well, people started accounting for the gravitational pull from galaxies outside the local group. That makes a difference.
Okay, the wider cosmic environment.
Right. And incorporating the cosmological constant dark energy, that actually tends to increase the estimated mass needed by maybe 10% or so.
Because dark energy pushes things apart, so you need more gravity, more mass to overcome it and bring M31 and the Milky Way together.
You got it. And they also account for the fact that galaxies grow hierarchically through mergers, which affects things too, often by comparing with those cosmological simulations.
So it's gotten quite sophisticated. But it still depends, crucially, on knowing how fast Andromeda is moving sideways, that tangential motion.
That was always the Achilles heel, the biggest uncertainty. Measuring that tiny apparent motion across the sky for such a distant object was incredibly hard.
Until Gaia.
Until Gaia. Gaia DR2 data really revolutionized this. Vander Morel and his team in 2019 used Gaia to track hundreds, even thousands, of individual bright stars in both Andromeda, M31, and its neighbor, M33.
Tracking individual stars in other galaxies.
Yeah. Relative to background quasars to get incredibly precise proper motions for the galaxies as a whole.
And what do they find?
They pinned down the center of mass proper motions much better than before. And interestingly, their results confirmed earlier, less precise hints from Hubble Space Telescope data.
Which were?
That Andromeda does have a significant tangential velocity, but not enough to avoid an eventual collision with the Milky Way.
So the Great Merger is still on billions of years from now, thankfully.
Seems like it, yes. And building on those better tangential velocities, Benesty and colleagues in 2022 refined the timing argument calculation again.
What do they add?
They accounted for the fact that the Milky Way isn't stationary either. It's actually moving towards the Large Magellanic Cloud.
Right. Our biggest satellite is pulling on us, like the moon pulls the Earth.
Exactly. It affects our motion relative to Andromeda, so you need to factor that into the approach velocity used in the timing argument.
Makes sense. So what mass did they get?
They ended up with two slightly different estimates depending on exactly which tangential velocity value they used for Andromeda, but both were around 3.1 to 3.4 trillion solar masses for the local group.
3-ish trillion suns. How does that compare to just adding up the known big galaxies?
It's pretty close, actually. If you just sum up the estimated masses of the Milky Way, Andromeda, M33, and the Large Magellanic Cloud, you get maybe 3.7 trillion solar masses, give or take, and the smaller galaxies add maybe another 0.7 trillion. So the timing argument result is in the right ballpark.
Okay, that's reassuring.
Yep.
Now, you mentioned the Large Magellanic Cloud, the LMC, pulling on the Milky Way. That sounds important.
It's turning out to be very important. The LMC is hefty for a satellite maybe more than a tenth of the Milky Way's own mass.
That's substantial.
It is. And right now it's flying past us pretty close, relatively speaking, about 50 kiloparsecs and moving fast, over 300 kilometers per second.
A close, high-speed flyby.
Yeah. And it's massive enough that its gravity is actually, well, perturbing the Milky Way. It's literally pulling our galaxy's disk slightly off-center from the overall center of mass of the Milky Way's dark matter halo.
Wow. So this small satellite is actually making the whole Milky Way wobble.
In a sense, yes. Peterson and Peñarubia used Gaia data in 2021 to show this. They found the Milky Way's disk is moving about 32 kilometers per second relative to the outer halo stars.
And the direction points back to where the LMC came from.
Exactly. It's evidence of the LMC's gravitational tug during this flyby.
Okay, so if the Milky Way itself is wobbling because of the LMC, that must mess with the timing argument calculation between the Milky Way and Andromeda, right?
Yeah.
Because that assumes a simpler two-body interaction.
Precisely. The LMC introduces a significant perturbation that needs to be accounted for. Chamberlain and colleagues did just that in 2022.
And what happened to the mass estimate when they included the LMC's effect?
Their updated total mass estimates for the local group came out a bit higher, actually, around 4.0 to 4.5 trillion solar masses. But importantly, they showed that if you didn't account for the LMC wobble, you'd overestimate the mass needed in the simple timing argument by maybe 10 or 20%.
Because some of the observed motion would be due to the LMC's pull, not just the total M31 Milky Way mass.
Exactly. It just highlights how interconnected everything is, even on these huge scales. You can't ignore the influence of even the satellites.
It's incredible we're refining the weight of our entire galactic neighborhood by understanding the dance between our galaxy and its largest satellite.
And Gaia's data is underpinning all of these refinements. Its precision is just unlocking new levels of understanding.
So wrapping this up then, this deep dive shows that figuring out the local group's mass is, well, it's complicated.
Definitely not straightforward. It involves these sophisticated methods, simulations, the timing argument, and it relies heavily on constantly improving data.
Especially for missions like Gaia. They're giving us the precise movements we need to feed into these models.
And these mass estimates, they're not just trivia, they're fundamental tests of our cosmological models, like SEDM. They help us check if our basic understanding of how the universe formed and evolved holds up.
It really makes you think, doesn't it? How we're learning about these vast cosmic structures, the whole local group, by watching the subtle movements of individual stars and galaxies interacting.
It's quite amazing, and you have to wonder, as our telescopes get even better, what other secrets are hiding in these motions? What else will we uncover about our place in the cosmos?